For this tutorial session, I have some questions based on the power series solutions. And the first question is x squared minus 1 y double dash plus 6x y dash plus 4y equals to minus 4. So we have to solve this and find the power series solutions. Okay, so assume that yx equals to summation n equals to 0 to infinity an xn, and then the differential will be summation n equals to 1 to infinity n an x to the power n minus 1. Here notice that n is starting from 1 because for n equals to 0 this yx term will be a constant, that is a0. So the differential of a constant will be 0. So here n starts from 1 and y double dash will be n equals to 2 to infinity. So it is n into n minus 1 an x to the power n minus 1. Again, if you notice that here n starts from 2 because the first term of this series will be this a1, and this is constant for this differential, and again you will get here uh, differential of this term a1 is 0. Okay, now you have to find the values of the coefficient an to solve this equation such that those coefficients satisfy the main equation which we are trying to solve. Okay, so let's substitute for y dash and y double dash in this equation, and so this will be x square minus 1 summation n equals to 2 to infinity n minus 1 an x to the power n minus 2 plus 6x summation n equals to 1 to infinity n an x to the power n plus 4 summation n equals to 0 to infinity an x to the power n equals to minus 4. Now look carefully. So in this equation, this term has x square minus 1, so we can expand it, and this x square into x to the power n minus 2 would become x to the power n. So this will be summation n equals to 2 to infinity n into n minus 1 n minus 1 an x to the power n minus summation n equals to 2 to infinity n minus 1 an x to the power n minus 2 plus 6 summation n equals to 1 to infinity n an xn plus 4 summation n equals to 0 to infinity an xn equals to minus 4. Okay, now we have to combine some terms. So let's see what can we do. Now look at this first term. For this, for n equals to 0, this term will be 0, and for n equals to 1 also, this term is 0. So therefore this can be written as summation n equals to 0 to infinity, right? Because for n equals to 0 and 1, even if we add it, 0 is what we are adding, so it won't make a difference. N into n minus 1 an x to the power n minus, and for this term, if we see, for this term, it's not x to the power n, it's x to the power n minus 2. So the power of the x has changed. So for now, let's keep it as like as it is. This will be n into n minus 1 an x to the power n minus 2, plus again for this term, in a similar way, if you see, for n equals to 0, this n will be 0, so this entire term will be 0. So instead of writing n starts from 1, we can also write n starts from 0, right? So n starts from 0 till infinity n an x to the power n, and the last term, the summation, already starts from 0, an x to the power n equals to minus 4. Okay, so this term and this term and this term, this third term, here I'm missing 6. We can combine these three terms, right? Because all are starting from summation n equals to 0 to infinity and have an and x to the power n. So let's write it as summation n equals to 0 to infinity n into n minus 1, plus from here we will get 6n, plus from here we will get only 4 an x to the power n, minus summation n equals to 2 to infinity n into n minus 1 an x to n minus 2 equals to minus 4. Okay, now we want these two terms starting from n equals to 0. So this is already starting from 0, but this is not. So in this, what we can do, we can replace n by n plus 2. If we do so, then the coefficient of the power of x in both the terms will be equal, right? So let's do it for this term. So this will become n equals to 0, because now n will be starting from 0 to infinity. But the other way to look at it is that we just say n plus 2 is equal to 2 now, so n equals to 0. So that is why it starts from 0. N will become n plus 2, n minus 1 will be n plus 1, a n plus 2. Now this coefficient is also changed, x to the power n, and along with this term, summation n equals to 0 to infinity n into n minus 1 plus 6n plus 4 an x to the power n. Right? Now we can combine both the terms, because the x to the power n is same. So let's combine 0 to infinity. Okay, so what will this be? The coefficient for x power n here in this term, this will be n square. I am opening the brackets, minus n plus 6n. So it will be plus 5n plus 4 an, right? And for this term, it will be n plus 2 into n plus 1 an plus 2. So now this is the coefficient of x to the power n on this. Okay. So now when these two equations will be equal, for these to be equal, we have to check the coefficient of x at left hand side and right hand side. So coefficient of x to the power 0. Let's say now in this case that is n equals to 0. x to the power 0 will be 1, so this will be a constant, and that constant should be equal to the minus 4. So what that constant will be, if we substitute n equals to 0 in this case, this constant term will become 4 an minus, and over here n will be 0, so this is 2 into 1, so 2 an plus 2, 2an plus 2 equals to minus 4. So it's not actually n is 0 here, and n is 0 here, so this will be 4k0 minus 2k2 equals to minus 4, and this gives us k2 is equals to 2a0 plus 2. So this is the relation we have got between two coefficients. And similarly, if we check coefficient of other powers, those all should be coefficient of other powers of x. Those should be 0 because here we don't have any x terms, right? Okay, so let's see what will be the coefficient of some x to the power k. What will it be? If we replace n equals to k in this equation, this will become k square plus 5n, 5k plus 4 ak minus k plus 2, k plus 1, a k plus 2, and that is going to be 0 because this is the coefficient of x to the power k, and there k is not 0. Okay, so now we can write this as k plus 4 into k plus 1, right? This can be written like this. So k plus 2 can be written as k plus 4 into k plus 1 divided by k plus 2 into k plus 1 ak. So this gets cancelled. Now what we have here is k plus 2 equals to k plus 4 over k plus 2. Okay. So this is the recurrence relation which we have. This is called recurrence relation. Okay. Now we have this. Now let's see for odd values. For odd values of k, what will it be? So the values of k will be now 1, 3, 5, 7 and so on till infinity. So for n equals to 1, we can write it as a3 equals to 5 by 3 a1. For n equals to 3, we can write it as a5 equals to 7 by 5 a3, which will be 7 by 3 a1. Similarly, for n equals to 5, a7 will be 9 by 7 a5 equals to 9 by 3 a1, and this will be 3 a1. So in general, what can we write? A odd terms can be represented by 2k plus 1, right? But this term will always be odd. So you see, when it is 1 here, this is 5. When this is 3, this is 7. So basically, what the pattern which you can see here, it's 2 times the number plus 3 over 3 times A1. Right? So 1. So 1 for the 1 will be 5. For n equals to 3 it will be 3. For n equals to 3 it's here. So for k equals to 2 it will be 2 to the 4 plus 3 7 this time. Okay. So this is what we have for odd values. Now for even values of n, let's say for n equals to 2, what we will have is a4 equals to 6 by 4 a2, which will be 6 by 4 2a0 plus 2. This will be 2a0 plus 3. Similarly, for n equals to 4, this will be a6 equals to 8 by 6 3a0 plus 3, because it will be 8 by 6 a4 and a4 is 3a0 plus 3, so we can write it like this 4a0 plus 4. And similarly we can write for a general even term. So in general a2k will be k plus 1 into a0 plus 1. See, this is 3a0 plus 1. This is 4a0 plus 1. So this pattern will carry on, and for a general term, for any general even term, that is 2k, so if you put any k here, this will be k plus 1 a0 plus 1. Now if we put this and this together, what we will have is the final power series solution. So putting this together, we have y of x equals to summation k equals to 0 to infinity k plus 1 a0 plus 1 x to the power 2k. So this is the even terms, plus now the odd terms. Odd term for summation k equals to 0 to infinity this 2k plus 3 over 3. 2k plus 3 over 3 a1 x to the power 2k plus 1. So this is the final power series solution of the given equation. So this is the odd term. Any doubts? Okay. So next I thought to tell you for an nth order homogeneous linear differential equation how we classify ordinary singular, regular singular points. So let us consider a nth order homogeneous linear differential equation. So it can be written as y n. This is a function of x plus 2 n minus 1 x y to the power. It's not y to the power, it's y differentiated n minus 1 times. It's a function of x and so on till then is a function of x, y differentiated 1 time x plus e0 1 x equals to 0, where y of k, that is y differentiated k times. This means this. Okay, y to the y k x would mean that y is differentiated k times. Okay, so now what are ordinary points? How do we define ordinary points? So a point x naught, where x naught is not equal to infinity, is called ordinary point if all the coefficients of this differential equation, that is p0x, p1x till n minus 1x are all analytic. Okay, in a neighborhood of x0. Okay, now what does it means for a function to be analytic? That function has derivative at each point in the domain, has derivative at each point and is single value. Basically, the limit at x equals to x0 exists for that particular function, then we say that it exists and is finite, then we say that it is analytic function. So this is the definition for ordinary points for any nth order homogeneous linear differential equation. Now let's see an example where y double dash minus e to the power x y equals to 0. Now here we have to see whether it is whether all the points in the real domain are they ordinary or not. So if we see, compare it to the general equation, the coefficient of y is p naught. So p naught x in this case is minus e to the power x, and it is analytic function, right? Because differential exists at every point. So every point x naught which is not equal to infinite is an ordinary point in this case, because minus e to the power x is defined. If you see this plot, this is x, this is y, then the plot will be something like this. X equals to 0, the value here will be 1, and it will asymptotically reach 0 at minus infinity. Okay, so this is analytic functions. If every point in the real domain are now ordinary. Now let's see another example where like x to the power 5 y triple dash minus 1 equals to 0. Now first write it in the standard form where the coefficient of the highest order is 1. So this will be y triple dash minus 1 by x to the power 5 y equals to 0. Now here if you see, we can write P0x as minus 1 by x to the power 5. Therefore, at x equals to 0, there exists a singularity. That is, this is not defined this function. So, but at except x equals to 0 and infinity, we are not checking infinity at this case. At this time, I will tell you later how to do it. All other points are ordinary points. Okay. Now, is it clear what ordinary points are? Any confusion?
Ma'am, at ordinary points, the we have single value derivative.
Derivative should exist and the value of a function should be single. It's not like, let's say, if there is some function like this. Okay, so but this function for any value of x, it has got only a single value. But if some function is like this, then for this particular value of x, it has got two values of y. So this should not be the case.
Okay, ma'am, got.
Okay. Any other doubts? Okay. If not, then I'll move on to the next definition, which is the regular singular point. Okay. So for regular singular points, uh, firstly the point will be singular, but we can classify it as regular singular. So if not all of p0x till p(n minus 1x) are analytic, but if all of x minus x0 to the power n p0x x minus x0 to the power n minus 1 p1 and x minus x0 p n minus 1, these are analytic. You know, neighborhood of x0. So in ordinary points, we were checking this function itself whether this is analytic or not. If it is not, then it is not an ordinary point. But in this case, we will multiply with these coefficients and we will see if it is if these coefficient modified are analytic or not. If they are analytic, then we will say that particular singular point is regular singular point. So let's see an example. X minus 1 y triple dash equals to y. So in standard form it will be y triple dash minus 1 over x minus 1 y equals to 0. So clearly if we see x equals to 1 is a singular point. Now we have to check whether this is regular singular or not. Okay, so this coefficient of will be P0. P0 is 1 minus 1 over x minus 1. For P0, what we have to check is x minus x0 to the power n. So here x0 will be 1 because we are checking regularity around this particular singularity. So minus 1 over x minus 1 is P0. So x minus x naught to the power n, P0x will be x minus 1 to the power n. N in this case will be 3 because it's a third order reaction. P0 is minus 1 over x minus 1. So this will be minus x minus 1 whole square. And in the entire domain, this is going to be analytic, right? Therefore, we can say that at x equals to x naught equals to 1, the given equation is that x equals to x naught equals to 1, it is a regular singular point. Let's see another example for more clarity. X cube y dash equals to x plus 1 into y. Now this will be y dash minus x plus 1 over x cube y equals to 0. Now if we see x equals to 0 is singular point. So we will check for regular singular point at x equals to 0. So in this case P0x will be minus x plus 1 over x cube. Okay, so x minus x0 to the power n P0 will be x minus x0 will be 0 in this case and n will be 1. Since it's first order, P0 is this minus x plus 1 over x cube. So this becomes minus x plus 1 over x square. Now if we see this again is not defined at x equals to 0. That means this is not analytic ring. Therefore, this for this particular equation x equals to 0 is irregular singular point. Is it clear? Any doubts? Okay.
Ma'am,
Yeah.
that x equal to 0 is a singular point. How did we find this?
So if you see this particular function, so at x equals to 0, is this function defined? 0. What will it be?
No,
Minus.
the
So this will
will be
be,
zeros.
yeah. So since this function is not defined, that means this gives us a singularity. So we call this point as a singular point. So if you see this equation, if you put x equals to 0 here, this term would vanish, right? But if the highest order term only vanishes, then that point is singular. Is it clear?
Yes, ma'am.
Okay. Okay, so I said that this is now irregular singular point. So basically, you would have got an idea what irregular singular points are. But just for the sake of completion, I will say its definition as well. So the point x0 excluding x0 infinity is called irregular singular point It is neither, so if it is neither an ordinary point nor regular singular, neither an ordinary nor regular, then it is called irregular singular point. So for all these cases, I was not considering infinity, but we can also classify uh, x equals to infinity as singular or ordinary or regular or irregular singular. So let's see how to do that. Classification of point x naught equals to infinity. So generally, how do we do this? We know that if something is infinity, if we inverse it, it tends to 0. So similar transformation we use here. So we do inversion transformation here. So we replace x by 1 by t. Now if we replace x by 1 by t, what will d by dx become? Minus t square d by dt. And what will d2 by dx square become? t4 d2 by dt square plus 2t2 d by dt, and so on. You can write down for higher order terms. So is, I hope this you can calculate this. Take x equals to 1 by t. How do we get this d by dx, t2 by dx square? If there is any doubt, please let me know now itself. Okay, that means it's clear.
Ma'am, that
Yeah.
DDX, please explain once.
Okay. Okay. So if you differentiate this x equals to 1 by t, what will it be? Dx. Uh, so you differentiate with dx. This will be 1 by t. 1 by t will be minus 1 by t square dt. Now you inverse it. So what will it be? 1 by d, 1 by dx, or you can write it as d by dx equals to, this will be inverted now, minus t square d by dt. So this is roughly a way to say this.
Excuse me,
Uh,
madam.
Hello.
Madam, it will be minus t power minus 2.
Yes, ma'am, minus t power minus 2.
Yes, ma'am.
Minus,
T power minus 2. 1 by t square will be minus t power minus 2.
yeah, so this is right, right?
Yeah, yeah.
Yeah.
dx equal
So
to minus t power minus 2 dt.
yeah, but here we are doing the inverse. So dt is now in the denominator, it's no more in the numerator. So this t square, so basically you do cross multiply over here and uh,
Yeah.
do this.
Operator.
Yeah, so basically you are
It's called
using an
operator.
operator thing. So this will be t to the power 2 only, not minus 2. See, if you write this, this will be dx equals to minus t to the power minus 2 dt. But if I'm writing this, then it will be minus t2 only, not minus 2.
After this, however, what we will do? Dx equals to minus t power minus 2 dt. After
Yeah.
this, what we will do?
Now we have to write it in this form of operator. So simply uh, just write it as like this, I would say. So this is now d by dx equals to minus t to the power. So this will also be inverted, okay. So this is now 1 upon t to the power minus 2 d by dt. So this is d by dx equals to minus t square d by dt. And when you have to do for d2 by dx square, so it is d by dx of d by dx. So basically this will be minus t square d by dt of minus t square d by dt. And
Okay, ma'am. Got, ma'am.
yeah, so you can do this in minus t square d2 by dt square, and this will be, so I kept this term and differentiated this. Now I'll keep this term and differentiate this, so minus 2t d by dt. So if you open the brackets, you will get this term.
Ma'am,
Yeah.
ma'am, that operator I did not understand. That D operator. What is
Okay.
the use of it?
Use of this d operator. See,
Excuse
this
me, madam.
d by dx is the operator.
If you take reciprocal on both sides, we will get the operator.
Sorry?
Uh, dx by dt, you will take cross product. Dx equal to some dt will
Yeah,
come.
we can write that
That
too
if you
also.
take reciprocal on both sides, you will get the operator.
Yes, we can,
It's not exactly reciprocal, but it is operator.
yeah. So basically, from till here it's clear. Or maybe I shall start from here then. Let's say this is dx equals to minus t to the power minus 2 dt. So you can write it as dx by dt equals to minus t square minus t to the power minus 2. So see, here when we were differentiating, we did not differentiate with respect to anything, right? We just operated. So on x it was operated with differentiated with respect to x. So this was the operator here then, and here it was differentiated with respect to t. Now we have to get it back it in this form. So basically, here you want this in the denominators only. So just see that this is d by dt, okay, and this operator is working on x, and you are getting minus t to the power minus 2. So let's keep this operator only. Then this will be d by dt equals to minus I. It's kind of inversion of both. You can say basically invert both these. Let's say you are inverting both of these, then you can write it as 1 by dx equals to minus 1 by t to the power minus 2 d 1 by dt. But there is nothing like this. It's actually the operator, but we write it in this form. So is it clear, Ravi Shankar?
Yeah. Yes, ma'am. Correct, ma'am.
Okay. Okay. Yeah. So basically, the idea to classify any point at x not equal to infinity is, since we can't work with infinity, we invert it and we work with 0. So we do inverse transformation here, and then everything we will convert it in the form of from d by dx to d by dt. So once this transformation is done, so you will get some differential equation, and then uh, classify for that point for t equals to 0. If you classify, let's say for t equals to 0, you check whether the point is ordinary or regular singular or irregular singular. and t equals to 0 would correspond to x equals to infinity. So that's how you classify any point of x not equal to infinity. Is it clear? Okay, so let's see with an example. It will become even more clear then. So consider these three equations. Okay, so this theory is there in a book, Advanced Engineering Mathematics for Scientists and Engineers by Bender and Carl Bender and Orzek. For more details, you can refer this book by these authors. So consider these three equations. Dy by dx equals to minus 1 by plus 1 by 2y equals to 0. So let's write it in this one. Dy by dx minus y by 2 equals to 0. Another equation dy by dx minus 1 by 2x y equals to 0, and the other equation minus 1 by 2x square y equals to 0. So for these three equations, we will check for ordinary or regular singular points mean actually. So what you can do is that first, because these are simple first order equations, we can solve them and see what these ordinary or regular singular points mean at that particular uh, function, the solution which you get. So let's look at these one by one. So for the first equation, this dy by dx minus 5 by 2 equals to 0. So what the solution will be? Uh, so simply you can write it in variable separative form. This will be 1 by 2 dx, right? Integrated on both sides. This is log of y equals to x by 2 plus constant I'm writing as log of c so that I can combine with this. Let's write it c inverse. Now let it be c only. Then this will be ln of y by c, because ln y minus ln c will be ln y by c equals to x by 2, and y will be some constant multiplied by e to the power x by 2. So this is the solution for this equation. Now let's see, in this case P0x is minus 1 by 2 and this is analytic. So that means that for this all points are ordinary. So in the given domain all points are ordinary. What does that mean? If you look at its solution, only at x equals to infinity, right? This goes infinite, otherwise it gives a finite solution. So that is what all these ordinary points mean. So the other equation, if you see, okay, let's see for
Ma'am,
x
previous
equals,
slide.
um, is it, you can see this. Okay, for
Yes,
x
ma'am.
equals,
Proceed, ma'am.
yeah, for x equals to infinity, let's see what this equation will be. So you do the transformation x equals to 1 by t. What this equation will become? This will become dy by dt plus y by 2t square. Simply by using the transformation I told you earlier, this transformation. So this differential equation, if you do this inversion, it takes this form. Now if you check for t equals to 0, this function 1 by 2t square, right? So this is non-analytic because even if you multiply with t, that is you check for regular singular point, that is x minus x to the power n p0, this will be t into 1 by 2t square. Again this will be 1 by 2t, and at t equals to 0, this is this will give us this is non-analytic, this will give us singularity. So this is actually an irregular singular point. Irregular singular. So we now know that x equals to infinity is irregular singular, and that is why in the solution that is reflected that at x equals to infinity, this y tends to infinity. So classifying these points as uh, ordinary or singular has some meaning. So now let's look at the other equation. Dy by dx minus 1 by 2x y equals to 0. Now if you look at this equation, so p0 will be minus 1 by 2x. So clearly x equals to 0 is singular point because this function is not defined at x equals to 0. Now let's check if this is regular singular or or irregular. So if you do this x minus 0 to the power 1 minus 1 by 2x, so this becomes minus 1. So this is analytic. So this is now regular singular point. X equals to 0 is regular singular. Now let's check for x equals to infinity. So do the transformation again, x equals to 1 by t, and you can get this in the this equation in the form of t. This will come out to be dy by dt plus y by 2t equals to 0. Okay. So again, if you check in this similar way, it's actually the same equation, only it's the signs and all, it's the same form. If you check for t equals to 0, then that will come out as regular singular. So in this case, both x equals to 0 and x equals to infinity are regular singular, and so that should be reflected in the solution of this differential equation also. So let's see what the solution is. Simply it's dy over 5 equals to 1 by 2x dx. Integrate. So it will be ln y equals to 1 by 2 ln x. Let's try this constant as ln c only. So this will be y equals to c root x. This is the solution. So if you see, when the points are regular singular, so this solution root x is also analytic except for these branch points 0 and infinity. Except for x equals to 0 and x equals to infinity. Similarly, we can check the last equation which we had, dy by dx minus 1 by 2x square y equals to 0. So here at x equals to 0, we know that it's singular. But let's check whether it's regular singular or irregular. So you do that x minus 0 to the power 1 minus 1 by 2x square. This comes out to be minus 1 by 2x. And this is non-analytic at x equals to 0. So therefore x equals to 0 is in this case irregular singular form. And x equals to infinity we classify, that will be x equals to 1 by 2, and this differential equation will become dy by dt plus 5 by 2 equals to 0. So if you see this function p0x, it's 1 by 2 and this is analytic. So this x equals to infinity is ordinary, and that should be reflected in the solution of this equation as well. So solution will be dy over y equals to dx over 2x square. So log y minus 1 by 2x plus constant. So solution will be c e to the power minus square x by 2. So this solution is also analytic except for this is minus 1 by 2x. Except for x equals to 0. So that is because x equals to 0 was an irregular singular form. Is that clear?
Yes, ma'am.
Okay. Then that's all for today. We close this session for now. See you next week at the same time, 6 p.m. on Friday. Thank you. And bye.
Ma'am, next class topic and what will be the topic?
So whatever will be covered in the week 5 of the lecture series, those will be the topic for the tutorials.
Okay, ma'am. Thank you, ma'am.
Okay, bye.
Ma'am, this slide for another 30 seconds. This slide, last slide, ma'am.
Do you want to see this last slide? This?
Yes, ma'am. For another 30 seconds.
Yeah. Okay, I'll close the session now.